Good morning, everybody. Today, my talk is going to be on Valleytronics, specifically controlling valley coherence in atomically thin semiconductors. And I'll be focusing on one particular class of these atomically thin semiconductors, also known as transition metal dichalcogenides. And I'm sure these have been making a lot of buzz in the past decade in in the quantum information and CMP communities, and I think they're more popularly known as their acronym TMDCs. So this work I did in my dual degree thesis in my final year at IIT was in collaboration with Dr. Pankaj Jha, who is a postdoc at Caltech, Professor Anshuman Kumar, my advisor, and another EP, uh, another recent EP graduate, Murli, who is currently a PhD student at the University of Luxembourg. So, okay, to get started, as I mentioned in uh, in the beginning, so these TMDCs are have been getting a lot of attention in the past few years because for quantum information processing because of one unique property they possess. So in their K space, the TMDCs have two degenerate but distinct values. So in which excitons can lie. And the unique thing about these values is that um, the exciton in these values couple to orthogonal polarizations of light. So if my exciton is uh, in the plus k valley, which is one of the degenerate values, it couples to right circularly polarized light as shown here. And if it's in the minus k valley, it couples to left circularly polarized light. So keeping all the technical terms aside, basically you can think of these as two states of a classical bit. So this the exciton being here corresponding to a 0 and the exciton being here corresponding to 1. But now it just doesn't behave like a classical bit because we can cause these two values to interfere. So that's where we get the quantum advantage. So as with any qubit, a good representation of the states are on the block sphere. So you can see, so one way of thinking about this is the z-axis here corresponds to our classical qubit states with the 1 and the 0. And any other state is some superposition of the 0 and 1 state. So for example, analogous to the plus x state, we have an equally weighted linear superposition of the plus k and minus k values. So this would correspond to plus x, and similarly this state would correspond to plus y. Now, why use these values as a quantum information bit when there are so many other systems out there, such as the Transmon qubit, which all of Google, IBM, D-Wave, and I think recently Amazon use. So one problem with superconducting architectures is that readout is a little hard. So currently the best readout technologies, which are Josephson parametric amplifiers, can handle readout of about only 10 qubits, and scalability as scalability becomes a big problem. So one advantage of using these TMDCs is that the state readout, basically the measurement, your final measurement, is very easy because, as I mentioned, these excitons couple to light, and all the information of the state is contained in the polarization of the emitted photons. And so I'm sure, as most of you know, superconducting architectures require very low temperatures. You have to go down to a few millikelvin for for number one to enter the superconducting state, and then to ensure that the qubits maintain reasonable coherence times. TMDCs, on the other hand, because these excitons have a large binding energy, and essentially what a large binding energy means is that they are stable at room temperature. They're not susceptible to thermal fluctuations, which are on the order of kBt. So kBt is about, of the order of millivolts. Here we're in the order of electron volts. So we're 1,000 times, the energy of these excitons is 1,000 times larger than thermal fluctuation. So we're really not going to be affected at room temperature. So that's another plus point for these TMDCs. So now if we're actually going to use these TMDCs as a qubit, we need to be able to control the coherence between them, or we need to be able to control the superposition between these plus and minus k states. So I need to, as such, be, if I want to develop some sort of technology with these TMDCs, I need to be able to make sure my state vector can go around the entire block sphere. So there broadly there have been there are two major ways to control the coherence between the valleys. One is with an external coherent field, so basically an external electric or magnetic field. And so as you can see here, you apply one light pulse here, you create an exciton in the k valley. So this notation here, k is plus k and k prime is minus k. So a lot of this notation will be interchanged, k prime and plus k minus k. So just keep this in mind. But yeah, getting back to the point, you can see here that you can excite you send a light pulse in, excite an exciton in the k valley, send another control light pulse in here, create a superposition, and then finally read out your state. But again, this requires you to actually send in external light pulses, which can be, so I mean, it's not experimentally hard as such, but then if you imagine scaling up these architectures to, finally building a quantum computer, you don't want, you don't want to have to all use external fields. So that comes to the second way of controlling coherence, and that is without an external coherent field. So in the year 2000, there was this pretty groundbreaking paper from G.S. Agarwal, in which he proposed that if you can create an anisotropic vacuum, basically an anisotropic vacuum is the radiative decay of dipoles depends on the direction the dipole is oriented in. So if I have a dipole in the x direction, its radiative rate gamma xx will be different from a dipole which is oriented in the y direction. In an isotropic vacuum, gamma xx and gamma yy you'd expect to be the same. So there would be no coupling between the values, but it turns out in an anisotropic vacuum, gamma xx and gamma yy can be different. So you actually do end up with some coupling between the two values, and then that is a way to control the coherence. And as you can see here, you don't need external fields here. You don't need, like a big experimental setup to generate a magnetic field or electric field. All you need is a simple heterostructure here. This anisotropic vacuum can be created through something called a metasurface, which I will come to in later slides, or an anisotropic polaritonic material. Basically, a material which can give you different optical conductivities in different directions, such as black phosphorus. So so now the main focus, this controlling coherence without an external coherent field is a relatively new, at least for TMDCs, it's a relatively new direction to explore. And it's only been explored for monolayer TMDCs. So just a single layer of the transition metal dichalcogenide and excitons that are right and left circularly polarized in the plane of the TMDC. And that has some problems. Just using monolayer TMDCs turns out there are quite a few limitations. And so the main focus of my work was extending this anisotropic vacuum analysis to interlayer excitons in TMDC heterostructures. So one TMDC layer stacked over another. So now why move to interlayer excitons, and what are the limitations with these monolayer TMDCs? So in a monolayer TMDC, if you remember the block sphere representation from my first slide, so S3 is again just the plus K state or the one state. S1 is the plus X state, or the linear superposition of 0 and 1, and S2 is the plus Y state. Another linear superposition, but with a different phase between plus K and minus K. So the problem with monolayers is that no matter what sort of control you use with an isotropic vacuum, no matter how much you change gamma XX or gamma YY, because these are decay rates, the form of the coupling, this coupling constant, is always real, and that causes your pseudospin state vector to always be stuck in the S1 S3 plane or DXZ plane of the block sphere. So no matter what you do, you can't really get out of this, and that isn't ideal for quantum information technologies. Secondly, it's very hard to, using monolayer excitons, it's very hard to scale up for future. I mean, it's very hard to scale this architecture up because you can't localize the exciton. So if you recall, where in the excitons are in one valley, so they're in one point, they're in a local area in momentum space, and as a result, they'll be spatially spread out through over a few unit cells in real space, and that makes it very hard to create an array of such excitons. But it turns out in heterostructures or using interlayer excitons, there are these things called Moiré lattices. So basically, a Moiré lattice is when the layer on top or bottom has a small relative twist angle, or is rotated slightly with respect to the bottom layer. So as you can see in the figure here. And what allows excitons to be spatially localized here is the Moiré potential. So because of this small twist angle, you can see that there is a valley here in which the exciton can be, the exciton is localized in. So this point corresponds to this point here in the Moiré lattice. So the exciton is localized. There's one exciton here, right circularly polarized exciton here. There's one right circularly polarized exciton here, one here, and so you can see here now that there's these Moiré lattices let us have an array of such interlayer excitons. And another motivation point for interlayer excitons is the decoherence time. So as you can see here, the decoherence between the valleys, or more commonly termed in the literature as intervalley scattering. So the intervalley scattering rate for interlayer excitons is much smaller than the intervalley scattering rate for intralayer or monolayer excitons. So that results in longer coherence times and hence more gate operations for interlayer excitons. So just to summarize what's happened in the, and give a few numbers to the interlayer and intralayer exciton. So the radiative lifetime of intralayer excitons is on the order of 10 picoseconds, and the radiative lifetime for intralayer is on the order of 10 nanoseconds. So there's it's 1,000 times, it lasts 1,000 times longer. Then the valley lifetime, which is the decoherence time, is again 1,000 times longer than the valley lifetime for monolayer excitons. State initialization is very easy. It's just you send in one photon, excite the system, and then okay, you have the state. That's for interlayer excitons, it's a little more complicated. You have to first excite the intralayer exciton or the monolayer exciton, followed by the hole then will tunnel through to the other layer, and this happens on a time scale of about 100 femtoseconds. So it's really fast. It's almost negligible on the scale of the radiative light time. And this will the hole will always tunnel because the interlayer exciton is the energetically favorable state. And it turns out that these interlayer excitons offer unique optical matrix elements. They offer more than just in plane right and left circularly polarized dipoles. So yeah, let me talk about now just interlayer excitons in these heterobilayers. So what I'll be considering here are commensurate heterobilayers. So what that basically means is there's no twist angle between the heterobilayers. There is just they're stacked in phase on top of each other. And what this because there's no twist angle between the even though there is no twist angle between the two layers, the analysis, even when there is a small twist to create a monolattice, is largely the same. There isn't any extra physics, at least in terms of the dipole moments of the interlayer excitons. So in another two, when I have no twist between the layers, there are two kinds of stackings possible. Either, so one is R stacking, in which the chalcogen atoms point in the same direction, I mean, relative to the metal atoms. And H stacking, where the chalcogen atoms point in different directions relative to the metal atoms. And then in K space, correspondingly, so if we go back to, if you recall from the first slide, for monolayer, there were the two values, where the plus K and the minus K. So in a monolayer, you'd have the conduction band plus K, conduction band minima and the valence band maxima would belong to the same value of the same layer. But now with interlayer excitons, we have, because the hole tunnels into the lower layer, we have the hole sitting in the valence band maximum of one layer and the electron sitting in the conduction band minimum of the other layer. So in R stacking, because they're in this, they have the chalcogen atoms point in the same direction, and by, so just take my word for it here, I won't get into the math, that the corresponding values of the conduction band minimum in the first layer and the valence band maximum in the second layer are both the plus K values. But in H stacking, because you can think that we've sort of rotated the bottom layer 180 degrees to get the chalcogen atoms pointing in different directions, the valence band maximum in the lower layer is a minus K instead of a plus K in R stacking. So now the only sort of now degree of tunability we have in such heterostructures is how much we can shift, we can translate one layer with respect to the other layer by. So essentially, if I were to take this, the top layer here and move it along this line corresponding to this arrow, I can have some, I can sort of tailor make the dipole moments of the interlayer exciton. So now one for the more experienced viewer here, one problem is that, okay, sure, in theory, I can, talk about moving the layers with respect to each other, but most heterostructures with, a random interlayer translation don't really exist in nature, and it's near, and it's almost impossible to create such heterostructures. So where then can we find excitons? And the answer is, again, we can find them in Moiré lattices. So if you look closely at the Moiré lattice, specifically this Moiré lattice unicell, and along the dotted line shown here, you can see that the sort of the atom, the layer stacking changes as we move along this line. So over here, if you look in this local region, it seems like the top layer and the bottom layer are stacked completely on top of one another. There's no interlayer translation between them. But if you go here locally, you can see that there is some interlayer translation between them. And as you continue going along this line, we come back to a full unit cell interlayer translation where the unit cell behind, if you were to imagine a unit cell behind this one in the peach color, that's come and sit on top, that's come forward now, and that is sitting on top of the lower layer. And so we're back to a completely perfectly stacked unit cell with no interlayer translation. So, and okay, and then you can ask, sure, but in the previous slide, I told you guys that the Moire potential minimum is here. So how am I going to get the exciton to actually come and sit here? And it turns out that you can tune the Moire potential with just a gate voltage. So if I were to, gate the top layer and the bottom layer, essentially, which is giving an electric field, a perpendicular electric field, I can shift the Moire potential minimum across this line, and hence then locally achieve any interlayer translation I want. Okay, so yeah, okay, so great, fine. So now we've understood interlayer excitons a little bit, but going back to the main problem, I'd say with monolayer excitons is that they were stuck in the S1, S3 plane, and that was a result of them being in plane circularly polarized. So if we go back a few slides. So the reason they're stuck in this plane is turns out to be because of the fact that monolayer excitons have in plane circularly polarized dipoles. So if interlayer excitons also have in plane circular polarized dipoles, then that's going to be pretty bad for us. We're not going to be able to overcome the stuck in one plane problem. But so intuitively, you don't expect them to be in plane circularly polarized because the electron and hole are spatially separated in the z direction. So you'd expect there to be some z dipole moment, and hence coupling to z polarized light. And luckily, it turns out that that's true. So you can see as a function of the interlayer translation, the one of the excitons. So we're looking at an H-type heterostructure. So you can see that the z part of the dipole moment isn't zero everywhere. And so that is sort of encouraging. So then that leads us to believe, okay, maybe we don't have in plane circular polarized dipoles, but we also need orthogonal dipoles because we need to map them to a state 1 and a state 0, and 1 and 0 cannot have any sort of overlap. So we need to make sure that the dipole in the plus k minus k and its corresponding conjugate minus k plus k have to be orthogonal. And it turns out that interlayer excitons have orthogonal dipoles, which aren't in plane circularly polarized. Instead, they're tilted. They have the axis has some tilt. It's not the z-axis. So those are pretty great results. So perhaps we can use these then and overcome the problem of being stuck in one plane of the Bloch sphere. So now, and it turns out that we have actually access now to the entire Bloch sphere subject to coherence times and coherence decay. But before we get into that, I'll now talk about how actually to couple orthogonal dipoles or orthogonal transitions in an anisotropic vacuum. So now let's go back to maybe physics 101 or basic undergrad physics, and what exactly we've all been told that you excite an atom, an electron goes into an excited state, then it decays out, it radiates a photon out, and then comes back to the ground state. And I'm sure a lot of us have questioned, okay, how exactly does the atom electron decay? How does it emit a photon? From where does this photon come? Because I mean, in high school and the first few years of undergrad, we were always told that dipole or charge and electric field coupling is typically given through d bar dot e bar. But for an atom in free space, there is no electric field. So how does it couple to photons? So it turns out that the reason for spontaneous decay or the de-excitation of an excited state atom is because of vacuum field fluctuations, the electromagnetic vacuum. So one analogy I can give to this is the harmonic oscillator, right? So we know that the harmonic oscillator is a good analogy for the quadratures of the electromagnetic field. And so the ground state of the harmonic oscillator should has an expected value of the position x is 0, but the wave function actually spreads over quite a few values of x. So similarly, the ground state of the electromagnetic vacuum, while it has the number of photons is 0, the electric field has fluctuations, and that is, in a sense, what causes spontaneous decay. So then that leads you to, then the next natural line of thought is that, okay, can we manipulate these vacuum fluctuations? And can we actually, get two orthogonal dipoles to talk to each other, which they otherwise wouldn't, because if D2 and D1 are orthogonal, D2 dot D1 is 0, and the typical dipole-dipole interaction, which is proportional to D2 dot D1, that would also be 0. So as I mentioned earlier, G.S. Agarwal in 2000 came out with this, groundbreaking paper in which he said that, okay, if you can, sort of manipulate the electromagnetic vacuum and make it anisotropic, you can get these two dipoles to talk to each other. And how does that work? So let's say we've excited a dipole, we've excited one state of our, 3-level system. So this is the plus k minus k or the plus k value, and this is the minus k value or the minus k plus k value, depending on H or R stacking. And if you remember, the two values are degenerate, so the energies are the same. So let's say now we've excited an exciton in one of those. We've excited one of the value excitons, and I believe there's a question. Abhay, are we taking questions now or after?
I think we can take after.
Okay. So let's say we've excited one of the value excitons, call that D1. Now because of this excitation, the vacuum field, the electric vacuum field will mimic the polarization of D1. And that's given by the imaginary green sensor, which is a matrix, times a row vector, which is the dipole orientation of D1. And that will give you the electric field. And I'm not going to get into the details of this math now, because that will take quite a bit of time. But if anybody is interested, you can refer. This is very neatly described in the Principles of Nano-Optics by Novotny. So yeah, basically this term tells you how the vacuum field behaves in the presence of D1 being excited. And in an isotropic vacuum, this vacuum field will mimic the polarization of D1, and hence the coupling D2 dot D1 will always be 0, and there will be no coupling. But now in an anisotropic vacuum, essentially what we're doing is we're making sure that the vacuum field doesn't mimic the polarization of the excited dipole, and hence D2 dot D1 isn't 0. And okay, how do we do this now? So if you recall, an isotropic vacuum, I mentioned that we're going to suppress, or we're going to change the radiative rate of a dipole, let's say in the x direction, as compared to the y direction. And okay, how do we go about doing this? So there are a few ways I had mentioned. You can either use an anisotropic polaritonic material such as black phosphorus, or something called a metasurface, which is so a metasurface is it's an array of uh, these artificial atoms. Basically, an artificial atom, by artificial atoms I mean small nanorods or metallic nanorods or nano antennas, which act as artificial atoms. And by arranging these artificial atoms, as per in different ways on a planar surface, you can tailor make, or you can control the response of an incident electric field. So what we want to do is okay, so to suppress, how am I going to go about suppressing the radiative rate for an X dipole, but let's say not change the radiative rate for a Y dipole? So if we go back to what I was talking about a few minutes ago, we know that the spontaneous decay rate is caused by d bar dot e bar, with d bar dot e vac, the vacuum field fluctuations. And if I can somehow, suppress the X component of the vacuum field, but leave the Y component unchanged, then my radiative rate in the X direction should get suppressed, but the radiative rate in the Y direction shouldn't. And I can actually achieve that with a metasurface. And the idea is really simple. So think about this metasurface acting as a concave mirror for X polarized radiation, which provides a pi phase shift at the mirror itself. So I have an incoming X polarized field, and it acts as a concave mirror. So it sends it back to the focus where the emitter is, and it gives it a pi phase shift. And because I've given it a pi phase shift here, it's going to destructively interfere with the incident electric field. And because it destructively interferes, and hence the X component of the fields as seen by the emitter is going to be a lot lower than what it would have been if the metasurface wasn't present. So in this way, I've actually suppressed the electric field, the X component of the electric field at the emitter. But if I if I look at any other polarization, either Y or Z, I'm going to let that act as a normal mirror. So I'm not going to focus the Y or Z polarized fields back at the emitter. So the emitter essentially sees the same Y and Z polarized fields as it would have without the metasurface. So only the X direction has been suppressed, but the Y hasn't. And with that, this one of the co-authors on my paper showed in 2015 that you can actually design such a metasurface which achieves this exact thing and will suppress the radiative rate in the X direction and leave the Y direction alone. Now I'll quickly talk about, since we're running a little short on time, I'll quickly talk about how one would actually go about designing a metasurface. So as I said, you have these nano antennas, which are artificial atoms, and you can control the phase of the reflected radiation field, and the phase I want to mimic is the phase profile I want to mimic on the metasurface is this, and X and Y are the coordinates on the metasurface, the inclinar coordinates, and D is the height of where the emitter is sitting at above the metasurface. So essentially, this is the phase profile required for a concave mirror, and this is the pi phase shift I want for destructive interference for the X polarized field. So once I've designed each sort of artificial atom or nano antenna, and tune the dimensions to get a certain phase of how it's going to reflect the field, I will arrange them on my metasurface so I can mimic the exact field that I wanted here. So you can see at the origin I'm close to pi, which is corresponding to X and Y being 0, which is what we wanted, and based on the arrangement of the other nano antennas, we have reasonably created the phase profile that we wanted. And because of this, we have a lot more suppression for an X dipole as compared to Y or Z dipole, and hence a smaller gamma XX than gamma YY and gamma ZZ. And we actually created an anisotropic vacuum. So now coming to the system that we proposed in my work, it was MOSE2 WSE2 heterostructure, which is sitting above the nano antenna based metasurface. And the values of gamma XX, the normalized gamma XX, gamma YY, gamma ZZ, we got were 0.1, 1, and 1. And these all have been normalized to the free space decay rate of this exciton. And okay, so now how do we go about modeling this, the dynamics in our heterostructure? So the interaction can be modeled as a 3-level B scheme. If you guys remember, the interlayer exciton sits in the electron sits in a different layer, the hole sits in a different layer. So these have been color coded corresponding to the layers. And there is some amount of coupling between the two excitons. There is some decoherence between the two excitons, incoherent decoherence, and there is an incoherent radiation, spontaneous radiation to the ground state. And so based on the interlayer translation, you can see that the coupling is non-zero because of the metasurface. In an isotropic vacuum, the coupling would have been 0 for orthogonal dipoles. And we are only interested in orthogonal dipoles because we need to make sure that D1 and D2, which correspond to the bit 1 and bit 0, are orthogonal. So D1, the dipole moment for D1 and the dipole moment for D2 must be orthogonal. And we had seen that there are 2 points in which we have these tilted circularly polarized orthogonal dipoles. So we've for this presentation, I've just focused on one of them. And so coming back to the main problem that we had with monolayer excitons is that the kappa was completely real, and because they were in plane circularly polarized, and as a result, they were stuck in the S1, S3 plane. And as you can see here, the imaginary part, so kappa here has an imaginary component too. And physically, what an imaginary part of kappa means is just the sort of phase of the vacuum field. So if kappa is real, the vacuum is purely real, the vacuum field has a certain phase. And if there's an imaginary part of kappa, that means the vacuum field has a different phase attached to it. So that's what it physically means, because I mean, it's very hard to think of a coupling rate being imaginary. So the coupling rate is given by mod kappa. It's something to keep in mind. But yeah, the main takeaway from here is because the dipoles are tilted, you have a non-zero imaginary part of kappa, which allows you to access the entire Bloch sphere. Now, if this were to be done experimentally, which was one of the main points of the paper, we wanted to propose something that could actually be measured in experiment. So if you recall, one of the motivations for using TMDCs for quantum technologies was that the readout of the state is very easy. And since the polarization of the emitted photons contains all the information, the sort of natural metric to use to quantify the coherence would be the Stokes parameters. And for experimental considerations, we've added incoherent bidirectional pump so that a steady state would exist, and we could actually measure you could actually see the trajectory of the the state. So it turns out that the steady state values of S1 are proportional to the real part of kappa by gamma in the absence of any decoherence or intervalley scattering. And S2 is proportional to the imaginary part of kappa by gamma. And this was what the monolayer was missing. This S2, because the imaginary part was 0, the S2 value was always 0, and hence it was always stuck in the S1, S3 plane. And so this is the one major problem that we solved by moving to interlayer excitons, is that now, okay, we have moved away from the S1, S3 plane and can access pretty much the entire Bloch sphere. And as you guys can see, and which is pretty intuitive also, a large intervalley scattering rate will kill the coherence or the values of the Stokes parameters. And so ideally we want to operate somewhere lesser than a normalized intervalley scattering rate of 1. And interlayer excitons provide just that. They're about 0.5, 0.1 to 0.5 on the order of that. So somewhere here. So that's still a pretty good area to be as compared to interlayer excitons which were here. Sorry, intralayer excitons which were here. Okay, so yeah, the main point of if there's one takeaway I want you guys to have is that tuning the anisotropic vacuum, basically changing the radiative rates in the x and y direction, allow you to control this the relative phase between S2 and S1, the steady state S2 and S1. And as you can see here, you have full access from minus pi to pi of the of this particular angle. So we have full access to the Bloch sphere, and this diagram is just representative of different trajectories for different values of gamma x and gamma y. Now, again, as from an experimentalist point of view, there are going to be questions. Okay, what about the internal quantum efficiency? Different samples, depending on how well they're made, will have different internal quantum efficiencies. So it turns out that the internal quantum efficiency only affects the purity of the final quantum state. The phase is largely unaffected. And interlayer excitons seem to, at least at a few measurements done on the internal quantum efficiency, they seem to have pretty high quantum efficiencies, greater than 50%. So as you can see here, the sort of area we're working in, the shaded region, is for values in between etas 0.5 and 1. They are pretty, it's not that bad. At least it's still measurable, the coherence. And as you can, maybe it's not clear from this diagram, but it's still, even with etas 0.5, as the normalized S1 to S0 is still 0.1, which is measurable, and S2 is 0.2. So a bad quantum efficiency doesn't, at least from an experimentalist point of view, doesn't kill any hopes of actually realizing this experiment. Then other experimental conditions are external factors. So how much of the actual light you can capture. You can't capture all of the emitted light because your objective lens is only so large. So for a dipole, so we're currently working on this, how to maximize photon collection efficiency. But just to give us a small idea, a dipole dipole oriented in this direction along the optical axis has a lower collection efficiency than a dipole oriented here. So that's good for us because the TMDC, well, good and bad for us depending on the orientation, how much the dipole is tilted in our interlayer excitons. So in a monolar exciton, because the dipoles are in plane circular polarized, they correspond to theta is 90. So the photon collection efficiency is higher than what it would have been for the Z dipole, but we will be somewhere here. So we'll have to see how many photons you can actually get and whether it will actually be possible to experimentally see this coherence. And other considerations are the external quantum efficiency. And yeah, I'm sorry, this is a little confusing. I should have mentioned external here. So how much of the photons are lost to lossy modes in the nano antenna? So for a toy model, we've taken an emitter above graphene, which is supposed to mimic the lossy material below, which causes an isotropic vacuum, either the nano antennas of the metasurface or black phosphorus. And you can see that as we're really close to the lossy material, our external quantum efficiency is terrible. We lose most of the emitted light to lossy surface waves. But as you go farther, the external quantum efficiency gets better. But as you go farther, the effect of the isotropic vacuum goes down. So you don't get as much as a suppression as you want. So we expect there to be a sweet spot, somewhere, hopefully with a reasonably high external quantum efficiency and a reasonable effect of the isotropic vacuum. So just to summarize, I know this was a very long and tedious talk. Interlayer excitons definitely seem to be better candidates for Valleytronics as compared to interlayer excitons. They have unique tilted orthogonal dipole moments, which offer access to pretty much the entire Bloch sphere constrained to decoherence. And the readout is really easy for such systems because it's just measuring the polarization of the photons, emitted photons. And one direction to look at is, instead of a metasurface, use black phosphorus because you can tune gamma XX and gamma YY by just applying a gate voltage. With the metasurface, once you design the metasurface and nano antennas, you can't change gamma XX and gamma YY. You have to redesign the metasurface. So for actual quantum control and in the future, if this becomes big, then people would want to explore these sort of heterostructures instead of metasurfaces. So just outlook, to sort of give my concluding thoughts on this field. It's a very new field. So I know I've made it seem, at least I hope I've made it seem like, okay, this is exciting, but there's still a lot of problems to overcome in actually addressing individual interlayer excitons in the Morey lattices, to overcoming decoherence. So do I think it's going to replace superconducting qubits or spin qubits or Gaussian boson modes for photonic qubits? I mean, it's unclear. There's no obvious answer here, and I think a lot more has to be explored, and it's definitely worth exploring. So thank you guys for taking the time out to listen to me.